Hello, National 5 chemists. It's Mr. Morton here. I hope you're all doing really well and are ready to get into some more chemistry. Today we're continuing on with some new learning and looking at Unit 3 Chemistry and Society. We've finished for now looking at metals. We've done all we need to know about our metals topic, and we're moving on to look at plastics. And here's what we need to know for our plastics topic. Learning intentions are on the screen right now. Not a whole lot of stuff, not a whole lot to learn at all, but there's a lot of a new terminology for it, some new jargon to get our heads around. We need to know what a monomer is, what a polymer is, what addition polymerization means, and also be able to bring in some of our knowledge from Unit 2 and drawing out different carbon structures to be able to draw these polymers, these monomers, and something called a repeating unit. So that's what we're going to look to get through in today's video. Now, just before we get into plastics, let's have a little think about some of these starter questions here, just to get our kind of brains in gear. I'll give you a chance now to pause the video, read through these three questions, and jot down an answer. So the first question here, these are all multiple choice questions from the National 5 2014 paper. First one is saying a reaction is endothermic if, well, we should be comfortable with the fact that endo and thermic is talking about a reaction where heat is taken in to the reaction. Heat is absorbed from the surroundings. So let's quickly jot through the answers here. Energy is required to start the reaction. Well, that could be true for an endothermic reaction or an exothermic reaction, so A is not correct. Heat is released during the reaction. No, that's the total opposite. That would be an exothermic reaction. C, the temperature drops during the reaction is the correct answer here, because if the endothermic reaction is absorbing heat energy, which it does, then the surrounding environment, the surrounding temperature will drop during the chemical reaction. D would be true for an exothermic reaction, like a fire, where heat is given out and therefore the temperature would increase. So endothermic reaction, temperature drops. Which of the following metals will not react with a dilute solution of hydrochloric acid? Well, this is one of our three reactions of metals that we need to know. Acid plus metal will give us a metal salt plus hydrogen gas. A metal will only react with acid though if it is above hydrogen in the electrochemical series. Now we can go to page 10 in our data booklet, look at these four metals and see which one is not above hydrogen. Copper is below hydrogen in the electrochemical series, therefore will not react with an acid. Iron, magnesium, zinc are all above it, will all react with acids. So the correct answer is A, because copper is below hydrogen on the electrochemical series and will not react with an acid. And finally, question 16, which metal can be extracted from its oxide or its ore by heat alone? The least reactive metals are the easiest to extract and only require heat to extract them. We've got three extraction methods. We can heat it up, which is the easiest way. We can heat up with carbon powder, or we can use electrolysis. Now, what we're looking to do here is again look in the electrochemical series, see which one of these metals is right at the bottom or close to the bottom, because that'll be the easiest to extract. That'll only require heat to extract it. And so D, silver, right at the bottom of our electrochemical series, very easy to extract. Only need heat to extract it. Don't need heat and carbon, definitely don't need electrolysis, so the correct answer for this one is D. Well done, guys, if you got these questions correct. Okay, let's actually start plastics. Here's a little clip from Twig, which just gives us a little bit of background information and will set the scene for us to move on and to learn about all these different types of polymers and monomers, etc.
From toothbrushes to telephones, straws to spaceships, plastics are used in an enormous range of products and have been for the last 150 years. Though they can have very different properties, they're all synthetic materials called polymers, made in a similar way. The building blocks of polymers are small molecules called monomers, obtained from crude oil. The carbon atoms are joined by double bonds, but these can be broken to create single bonds, free to join other carbon atoms and form long chains called polymer molecules. This process is called polymerization, and the resulting polymers are the main components of plastics. Plastics often take their name from their component monomers. So ethene becomes polyethene or polythene. Similarly, styrene becomes polystyrene, and propene becomes polypropene. The reason plastics have different properties isn't just because they're made from different monomers. It's also down to how their polymer chains are arranged and held together. Take high-density polythene, for example, with straight polythene chains packed closely together, producing a high-density material. It's rigid, strong, and used to make plastic milk bottles. But branched polymers cannot pack so easily, so the density is low. And this lighter, flexible material makes plastic bags. The force of attraction between polymer molecules also has an effect. The stronger these intermolecular forces, the tougher the plastic is, and the higher its melting point. Polymer properties can be changed by adding certain ingredients. Cross-linking agents create strong covalent bonds between adjacent polymer chains, making the material stiffer, stronger, and more heat resistant. Plasticizers, on the other hand, make the material bendier by getting in between the chains and weakening the forces of attraction between them. Synthetic polymers have only existed for about 150 years, but it's hard to imagine a world without these amazingly versatile materials.
As I'm sure we heard from that video there, plastics have been very useful in modern life for years and years now for a number of different reasons, but mainly because they have loads of useful properties. They're relatively easy to produce, they're cheap to produce, they're lightweight, they're waterproof, etc. But of course there's the issues with plastics as well, which I'm sure we're all aware of. They are man-made materials, so they're classified as being synthetic. And as also stated in that little clip there, the plastics are made from crude oil. And we talked quite a lot about crude oil in Unit 2. We talked about the fractional distillation of crude oil, the different fractions, the trends in the fractionation column. One of the products produced from crude oil is plastics. And here's now where we're really starting to get into the proper National 5 content, is talking about the structure of plastics. How are they made? What are they made from? And they're made from molecules called monomers, which can be added together to produce really long strands, fibers called polymers, which make up the plastic. So there's our first kind of little bit of key information there about plastics. These monomers, these polymers, we need to know what they mean, we need to know how to draw them and what they're made up of. And to join together monomers into a polymer to start to make a plastic, there's a specific type of chemical reaction, which is called a polymerization reaction. Now we'll look at a specific type of polymerization reaction called addition polymerization. So there's a lot of keywords we're throwing at you now. Now, as we said, plastics are synthetic materials. They're made up of lots of different fibers, made up of these giant molecules, and these giant molecules are made up themselves of thousands, if not hundreds of thousands, of smaller molecules called monomers. So here we've got a kind of visual example. These are our monomer units. Now, monomer is, I suppose, if we translated it from, I think it's the Latin, mono means one, and mer means unit. So a monomer is just something with one unit. And this is what we have. We've just got all these little balls, which are just one units, or monomers. If I join all these monomers together in a polymerization reaction, I'll get a nice big long polymer chain. Now polymer means many, mer, remember, just means unit. So polymer is many units joined together, monomer is just one unit. And that's a polymerization reaction. We're joining together monomers to make polymers. And as I said, poly means many. So their names fit. They're quite good descriptions. Monomers a good description, polymers a good description, and polymerization is a good description as well. So let's look at this idea of addition, polymerization in a little bit more detail now, turning monomers into polymers. So what are the kind of main key points of addition polymerization? Well, as I said before, monomers into polymers. That word monomer, if we take the mono part, means one, and the mer means unit. So we're turning one unit of something into lots of, or many units. So essentially we're just joining together loads of monomers to make a polymer. This is specifically an addition polymerization reaction. There's different types of polymerization reaction, but we're only focusing on one addition polymerization reaction. And we've talked about addition reactions before from Unit 2. If you have an addition reaction, we need to have a carbon to carbon double bond. That is very important. For us to undergo addition polymerization reaction, our monomer must contain a carbon to carbon double bond. And essentially, all we're doing is we're adding together these monomers, these carbon to carbon double bonds, to produce a long chained polymer. Now, when we're drawing out polymers, we only have to add together 3 monomers together. That's it. Now, plastics and polymers in real life, there's hundreds of thousands of monomers that make them up. We'd be there forever trying to draw them all in. We only need to draw 3 monomers to make up a polymer. That's it. Right, let's look at an example here then of drawing out a polymer from our monomer subunits. Here I'm wanting to look at the example of making polyethene. Now, something we've not talked about yet is naming polymers. It's very straightforward. If I'm wanting to produce the polymer polyethene, I need the monomer ethene. And what would be the name of the polymer produced when I used ethene? All I do is stick the word poly on the front of the monomer. So if I've got ethene, I would produce polyethene. If I had propene, I would produce polypropane. So that's how it works. You just stick on the word poly in front of the name of the monomer. So the monomer we're using in this example is ethene. We should know how to draw ethene. Eth tells me it's got 2 carbons. It ends in ene, telling us that it is an alkene. It is unsaturated and contains a carbon to carbon double bond. And once we've given every carbon 4 bonds, we'll have 4 hydrogens. So there's ethene. This is the monomer we'll use to make polyethene. Now, as I said before, if I'm making a polymer and I need to draw it out, like I'm doing in this example, I want to draw out what polyethene looks like, I need to join together only 3 of my monomers. So there's 1 ethene, there's a second ethene, and here's our 3rd monomer, ethene. I've not joined them together yet, I've just got the 3 of them lined up next to each other, ready to join together. So it's an addition polymerization reaction, which means that these carbon to carbon double bonds are going to break and we're going to join together these monomers to produce our polymer. So let's start that off by breaking these carbon to carbon double bonds by removing one of the bonds in the carbon to carbon double bond. And now we've got some carbon atoms which are only making 3 bonds. They want to make 4. So these monomers will want to join together because we've broken this carbon to carbon double bond. This carbon here has only got 1, 2, 3 bonds. It needs a fourth, and the easiest way for it to do that is to join to this monomer where it's next to. Now it's got 1, 2, 3, 4 bonds. So does this carbon. This one's only got 3, so it needs another bond to our third monomer. And now it's got 4, so does this one. And what you'll probably notice is that these carbons at the start and the end of the molecule, they've only got 3 bonds. And there's nothing else here, or at least we've not drawn anything else to either side. What you do need to do is to put in an empty bond. I like to think of it as like a little wing, if you will, sticking out either side. It's not joined to anything. I'm not going to write anything else at the right hand side or the left hand side. But what this does is it implies that all we've done is drawn a section of this monomer. There's, as I said, there's not just 3 monomers in this polymer, there's hundreds of thousands. We're only drawing 3. There's loads more on this side, and there's loads more on that side that we're not going to have to draw and do not have to draw. But to indicate that, we have to put in these little side bonds, just telling the person viewing what we've drawn that there's more to the story than what we've put down on the paper. So that's the kind of skill that we need to be able to do, to change from a monomer into drawing a polymer by adding 3 of them together. Important things to note there: we're breaking the carbon to carbon double bond, we're joining 3 monomers together to make the polymer, and we need to put in these side bonds once we're finished. And again, to name the polymer, I just simply put in poly in front of the name of the monomer. Okay, let's look at another example now, changing from a monomer into drawing out our polymer by sticking or adding together, rather, 3 monomers. Monomer this time is propene. Prop tells me I've got 3 carbons. This is going to be an addition polymerization reaction. I need to have a carbon to carbon double bond, and I can tell that because this is an alkene, ends in ENE, and the rest of my hydrogens I can put on together to make sure the molecule is complete. Now, when we're drawing out monomers, there's a specific way that makes your life so much easier than drawing it out like you normally would. If I asked you to draw propene, this would probably be the way that you would normally draw it. However, when we're drawing monomers and wanting to add them together, I think it's always a lot easier to try and draw it like an H, if that makes sense, where the middle of the H is our carbon to carbon double bond. So if we looked at the example that we did previously, where I had my ethene. Now that kind of looks like an H already, which is quite nice. I mean, if you draw ethene, it's the way it's going to look. However, propane does not look like an H. It's like a kind of straight line. And I want to kind of really, before I do this question, make it look like an H with that carbon to carbon double bond in the middle. So instead of drawing out propene like this, where I've got this kind of methyl part at the end here sticking out to the left, if I instead draw, instead of this CH3 sticking out to the left here, if I just draw it coming down like this, it looks a little bit more like an H. It looks a little bit more like the ethene monomer that we used before. And that's the easiest way for drawing out these polymers from monomers. We need to try and get the monomer in the correct position, if you will, before we get into this. So let's just redraw our propene. We've got our carbon to carbon double bond in the middle and our H structure, for want of a better word. This is definitely propene. I've got 1, 2, 3 carbons. I've just tried to draw it in that H structure. Now, I'm wanting to produce the polymer from propene. This is going to be called polymerization. propene, because I just put the word poly in front of the name of the monomer. And again, to produce or to write a polymer, I just need to add together 3 monomers. So there's one of my propenes. There's our second propene. Again, each one has 3 carbons, but I'm just drawing it in this arrangement to make my life a little bit easier when drawing them or joining them together. And there's our 3 monomers that I'm going to use to draw out this polymer. It's an addition polymerization reaction, so I need to have this carbon to carbon double bond. As we looked at last time, the carbon to carbon double bond is going to break. I'll rub that out for each one. And now these monomers can quite happily join together. I've got my 3 monomers joined together, and let's not forget these little wing bonds at the side, just to indicate that there's more to the story than just these 3 monomers in this polymer. Hundreds of thousands of monomers to make a polymer, we just need to draw 3, but to indicate that there's more, we need these bonds at the side. Another type of question that we can be asked is essentially doing this process in reverse. Instead of starting with a monomer and producing a polymer, they could give us, like they have in this example, a polymer and ask you to draw, well, what is the monomer used to make this polymer? Now, again, if we remember that these polymers are all produced from 3 monomers, when we draw them out like this, then I can split this up into 3 parts. 1, 2, 3, 4, 5, 6 carbons. If I split this like this, here's my 3 monomers that were used to produce this polymer. And all I need to do is to, I suppose, just work backwards and draw out what the monomer would look like. We've got 2 carbons, as I've got here. Let me draw that bond a little bit better. There's a fluorine molecule on the first carbon, and the rest of them are just H's. Now, important point here that we really need to remember is that all of these polymers were made by an addition polymerization reaction. Now, that tells us that every single monomer that we're going to work with must have had a carbon to carbon double bond. So when we're going back from a polymer into a monomer, we need to make sure that our monomer has that carbon to carbon double bond. Let's look at a final example here. Similar to the one that we've just looked at, we're starting with a polymer and we have been asked to draw in the correct monomer that it was made from, and also something called a repeating unit that we've not talked about yet, but you can be asked to draw a repeating unit, and we'll talk about the difference between this and a monomer. Let's start though with drawing the correct monomer used to produce this polymer. We know that polymers are made up from 1, 2, 3 monomers. They're all the same. So we're looking at our monomer used to produce this polymer having our carbon to carbon double bond and all the exact same 4 groups. So we've got a CN part up here, a H, another H, and a C2H5. So here's our monomer. Remember, this polymer was made by addition polymerization reaction. That means the monomer must contain and will always contain a carbon to carbon double bond at its center. And if we draw it out in this kind of H arrangement, it makes our life a little bit easier. So there's the monomer that they've used, and they've joined 3 of these together to produce this polymer. The repeating unit, different from the polymer, a little bit easier, in fact. Different from the monomer, I should say. Different from the monomer. The monomer contains a carbon-to-carbon double bond. The repeating unit is more just asking you to look at this polymer and to to write down exactly what is being repeated each time. And we've kind of already done this, and you can see it now by putting in these lines across our polymer. Now by doing that, it makes it a little bit more easy to see what's being repeated each time. And what is being repeated is this carbon to carbon with, again, H is up here, Cn there, H down there, and this C2H5, and I'll put a bracket around that. That's how we draw out a repeating unit. This is what is being repeated each time. It's almost like you're taking a snapshot, a little picture. You're copying, pasting part of the polymer and just drawing it out in this fashion here. Again, for the repeating unit, we need to have these side bonds to indicate that there's more to the story over here and over here, but we don't need to draw it in. We're just drawing out one thing that's been repeated each time. The monomer, however, does not have these side bonds, because that would mean these carbons have 5 bonds, and that would be wrong. The monomer must contain a carbon-to-carbon double bond. Now guys, there's a lot of jargon being thrown at you in that video. Polymers, monomers, repeating unit, polymerization reaction. Make sure you watch this through probably a couple of times so you're comfortable with what is a polymer, how to draw a monomer, how to draw repeating units, etc. And have a go at the exercise number 1 in that booklet with lots of different examples on what we've just talked about.